All right. Good afternoon. So today we are scheduled to talk a little bit about chi-square, and we will in a moment. But before we get to that, I just want to share a few quick announcements for you. So for this weekend, what you have due for this Sunday night, you have due quiz 12 and the bonus assignment for the class if you choose to do that. Now this is different from the exam 2 bonus opportunity. This is just a bonus of up to 20 points that gets added wherever you need it. So this is a great opportunity. It's also a good review for the final. I'll share that with you. What I'm going to do with that bonus opportunity is I'm going to give you an additional week to do it. So it was going to be due this Sunday 5/2. It will now be due Sunday 5/9. It will now be due Sunday 5/9. The quiz 12 will still be due this Sunday, but that's all that'll be due this Sunday. Then the following Sunday, it'll just be the that bonus opportunity if you choose to take advantage of it. And I'll get that posted for you early so that if you want to do it earlier, you can. Okay, so that'll get posted pretty soon for you. The other thing I wanted to share with you is that, well, a few more things. This Wednesday, of course, is your exam 3, as I noted in my email to you guys. And so we won't be meeting this Wednesday. You'll have the exam. It'll open at 5. It'll close at 11:59 p.m. You have 75 minutes to take it once you start. However, the other point I wanted to raise is regarding our meeting next Monday. So next Monday was written in red and was a putting it all together day that is for attendance credit. So what I'm going to do with that day is make it an optional day. I won't really plan on lecturing much. I might pull a few notes together for you. It might be just a little small tidbit there. Mostly it'll be open questions. And what you can do is it's going to be a bonus attendance day. So this attendance day can take the place of something that you missed. Okay, so if you missed one in the past that you wish you didn't and you want to make it up, here's your opportunity to make up one attendance day. Okay. And we have a question coming in. Okay, so question about the format of at least exam. Let me share exam 3 and share the final exam format for you as well. For exam 3, it'll be the same format, up to, which means it could be less than 25 questions, of which up to 2 maybe fill in the blank. So that could be 0, 1, or 2. That's exam 3, and that's been how we've done the first 3 exams. For the final exam, it will be a potentially a little bit longer. It will be up to 40 questions. Up to 40 questions, and you might have up to 3 fill in the blanks. So only one more fill in the blank. Now a couple more questions have come in since I've been chatting with you, so let me address those as well. Yes, you will be doing a cheat sheet for the 3rd exam as well. So the 3rd exam will be a cheat sheet that you'll need to do. And would Monday be the last Zoom meeting if we decide to come? So next Monday is that optional bonus attendance day. Then Wednesday is a plain old optional question day, and that's up to you if you'd like to come on Wednesday. Okay, no extra attendance credit. It's just for any last questions you want to ask or touch base about. Okay. All right, so that's how we're looking in terms of our timeline. Thanks for chatting in all those questions. They're all good ones. If you have additional questions, please continue to chat in. I'll get to them as I can. But hopefully that gives you some sense of what we're doing. So like I said, we'll do chi-square today, exam Wednesday. Next week, Monday, is that bonus attendance day. That's optional, and we'll cover some questions and see if I have anything to summarize for you guys. Probably not much. It might just be, like I said, a little bit. And then the last Wednesday of our meeting time would be optional, just for additional questions. Okay. So let's talk a little bit about chi-square. Now, you hopefully recognize up here the rock, paper, scissors, lizard, Spock piece. Back from way at the beginning, I believe it was one of our first activities, and back from the probability lecture, where we were talking about this game. We talked about rock, paper, scissors, the game. Is it fair? Yes. And how does it come out? You get about a third wins, a third draws, and a third ties. And then we talked a little bit about rock, paper, scissors, lizard, Spock, and you actually played some games of this to determine the probabilities there. So if you don't remember, let's look. Let me share my computer sound. Otherwise, this won't go well. There we go. I think I shared it. Yes. And then let's go ahead and review rock, paper, scissors, lizard, Spock. I hope.
I'll tell you what, how about we go rock, paper, scissors?
No, I don't think so. Anecdotal evidence suggests that in a game of rock, paper, scissors, players familiar with each other will tie 75 to 80% of the time due to the limited number of outcomes. I suggest rock, paper, scissors, lizard, Spock.
What?
It's very simple. But scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard, lizard eats paper, paper disproves Spock, Spock vaporizes rock, and as it always has, rock crushes scissors.
Okay, I think I got it.
Rock, paper, scissors, lizard, Spock. Oh.
Okay, so when we're talking about rock, paper, scissors, lizard, Spock, we can talk about null hypotheses and alternative hypotheses. So I don't know if you recall from way back at the beginning of the semester, but what we learned through using some probability is that wins, losses, and draws typically come out with 40% wins, 40% losses, and 20% ties. So, and that's kind of what they said in that little clip there. They were remarking that you're more likely to get a tie with rock, paper, scissors, that was 33%, versus rock, paper, scissors, lizard, Spock, where you only have 20% ties. So this game might be slightly better to avoid the ties. Now, let's suppose for fun, and we're not going to actually go through and play it again today, but let's for fun say we did. Okay, let's for fun say we broke out into groups of twos, and you all played additional games of rock, paper, scissors, lizard, Spock. And let's say you all played 15 games and that there was 10 groups. Okay. Well, our alternative hypothesis would be that you guys would be different from what we would naturally expect. What do we naturally expect? The 40%, 40%, 20%. And maybe I might make the argument that because you guys are all in a similar class, maybe you'll have, and your knowledge of probability and all, I might make up something here that says that I expect you guys to have more ties. Okay, so I would say that wins, losses, and ties will occur with different frequencies than the standard expected above. Okay, so one question that we always have to answer is, what is the expected frequency when we're doing chi-square? And the way we calculate it, if you haven't gotten to that lecture yet, because it's not due for a little while, is that we take our total n times the expected, which is based on our null hypothesis for each cell. So what I'd like to do with you guys is go through and show you how that would work. Okay. So again, let's make this assumption that there were 10 groups of 2 people each playing, right? And they each played 15 games. So 10 groups times 15 games, we would have 150 different possible answers. 150 total n, 150 total games, I guess I could say. Okay. So the way we would get our expected frequency is we would take the 150 for wins. If we want to do it for wins first, 150 times 0.40. And if you did that out, it would equal 60. 150, sorry, times 0.4 would give you 60. Next, we're going to do the expected frequency for losses. Now, the expected frequency for losses is quite the same, because it's also that we expect 40% losses just like we expect 40% wins. So what's 40% of 150? We take 150 times 0.40 and we get 60. And finally, let's look at the expected frequencies for ties. Again, what do we expect? 20%. That's what remains. We had 40%, 40%. What remains is 20%. 20% of 150, or 0.20 times 150, gives you 30. Gives you 30. So that's how we get our expected frequency calculations. Okay, let's take the next step. Okay, so this just shows you how you would actually play the game. We've talked through that before. And then we get into how we would actually calculate a chi-square for goodness of fit. Okay. And we already talked through the expected frequencies. And that is our E in this formula. So imagine a big OR right in the middle here, okay, between the FO minus FE and the O minus E. There's a big OR because these are 2 different formulas you might see out in the wild for chi-square. I kind of like this one on the right. I think it's a little bit easier, but whichever way makes you feel comfortable is perfectly fine. And let me read out this formula to you. It's observed frequencies, or O, minus expected frequencies, or E, squared, divided by the expected frequency for a cell. And then we do that for the number of cells we have. In our case, we'd have 3 cells, 1 for win, 1 for losses, 1 for ties. Okay. So let's play around with our data a little bit, and we'll pretend that, like I said, we're going to pretend we've run this. We have 150. Each of you played 15 games in pairs. We have 150 games, and we'll look at what we got. So for the wins, let's just start at the beginning here. Let's say there were 50 wins, 50 losses, 50 ties. Okay, so that's what it all came away with. See, I was right. I thought you might have more ties, and you did. You had more ties than what might be typically predicted, but we don't know if that's significant yet. So how are we going to figure this out? We're going to take the 50 observed minus the expected, square that, and divide by the expected. So now with that knowledge, let's look at the wins. Wins, 50 minus expected, remember we said that would be 60, equals negative 10. We're going to square that. Negative 10 times negative 10 gives you 100. 100 divided by 60, that's again dividing by the expected on the bottom, equals 1.6667. Okay, now let's do the losses. So let's go backwards one more time just to make sure we're kind of following this through. Again, we had 50 observed minus 60 expected, which is negative 10, squared is 100, divided by the expected, which is 60, gives us 1.6667. And here's that. Okay, so we've been a little off on our wins, a little off on our losses. Let's see how we are with the ties. Now we've gotten 50 again, but this time it's minus 30, because that's how many ties we expected. So 50 minus 30 gives us 20. 20 squared gives us 400. And 400 divided by 30 gives us 13.3333. So again, I'll show you one more time to follow through with this example. 50 observed minus 30 expected squared. So 20 squared is 400 divided by the expected, which is 30, gave us 13.3333. Okay, now remember this symbol over here, it means add them all up. That summation sign means add them all up. So we've got to add up those three numbers we just got. Oops, sorry, wrong way. So we're going to take the 1.6667 plus the 1.6667 plus the 13.3333. And if we added that up using our calculator, we would get 16.6667. Okay. So I see a question coming through. Let me address that before. Yeah, great question. So this is actually being recorded right now. So I am happy to share the recording with anyone afterwards if you'd like to watch this again. I do go through this in the chi-square lecture, but if you'd like to see this, I'll be happy to share the recording with you so you can take a look at this as well. Okay. So yeah, no problem. So now I want to go back and talk about degrees of freedom. Okay, we've got our chi-square number, 16.6667. Now let's talk about degrees of freedom. Let's not go forward, let's go backward. Okay, degrees of freedom is C minus 1, where C is the number of categories. How many categories did we have? Well, we had wins, losses, and draws. 3 categories, minus 1 is 2. So our DF is 3 categories, win, loss, draw, or win, loss, tie. Minus 1 is 2. Okay. So we have a chi-square and we have a DF. And that's enough really to go, as long as we know our alpha, it's enough to go into our chi-square table, which I'll show you right here, to find the appropriate number to which to compare. So I'm going to say our alpha was 0.05. So if we go down to 3 under the 0.05 significance level, we get 7.815. This is the number to beat. By the way, the nice thing about chi-square, this is also true for ANOVA. There are no negatives in the table. It's all positive numbers, right? That's unlike the Z and T, where you could have positive or negative numbers in the table. With the ANOVA, everything's always positive, and with the chi-square, everything's always positive. Okay, just thought I'd share that. Good question. So the The DF is 2. I apologize. Thanks for pointing that out. Yeah, I was just showing you 3, but the DF is actually 2, so I apologize. DF is 2. The number we're comparing to is 5.992. Number we're comparing to is 5.992. So we go back, we ask ourselves, does 16.6667 beat 5.992? The answer is yes, it does. There is a significant difference. So in our example, the 50-50-50 responses for wins, losses, and draws is quite different from our null hypothesis, from our expected of 60, 60, 30. Okay. All right. So, again, thanks for pointing that out. I just want to highlight it one more time since I did foul up that our DF is 2. The number we're trying to beat is 5.992, and we clearly did with 16.6667. We can reject the null hypothesis. This is significant. We can reject the null hypothesis. This is significant. Okay. So, I am going to share this, so don't, and also this is going to be available on your lecture, and this is also going to be available as a handout, so to speak, as a PDF file that you'll get a copy of on D2L. So don't scurry to write all this down. You're welcome to, but there's no reason you have to. So what I want to do now, because that's all I really wanted to share about chi-square, okay? That's the chi-square piece. What I want to do now is walk you through all of the tests we've talked about, because that was our last test, okay? And I want to show you what's different about these different tests, how to know which one you have. Okay, what makes each one unique so you know which one you've got. So this is our comparison of tests. There's something in common about all of the tests on this page, and that's why I put them all on one page. Specifically, they all have one continuous variable. Our dependent variable, I don't know if you've caught this before, but your dependent variable for each of these tests was always continuous. And for each of these tests, we were trying to detect differences. So if you have one continuous variable and you're trying to detect differences, you know you're on this page. And you might be thinking, well, that's nice, but now that's a lot on this page to narrow it down to. So let's start narrowing. Okay, first, there's only one test where you know the population variance, and that's the z-test. Okay, so if you've got a sigma square or a sigma x bar, you've got a z-test. Now, there's only 2 tests where you know the population mean, the mu, the average for the population. That's the z-test and the t-test for a single sample. So if you've got a mu, you know it's one of these 2, z-test or t-test for a single sample. Then you have to decide which one. Well, that depends on whether you have the sigma or not. That depends on whether you know the population variance. If it's known, it's a z-test. If it's not known, it's a t-test for a single sample. So that takes care of those 2, right? So now we're going into a land where we don't know the mu, where we don't know the sigma. Okay, so how are we going to tell the difference between the rest of these? Okay, well, if you have 2 scores for each participant, It's a t-test for dependent samples. That's the only one like that. That's the only test where you have 2 scores for each participant. If you have 3 or more scores for each participant, it's a repeated measures ANOVA. So we've talked through some different examples of both of these, right? We might look at blood pressure at the beginning of the semester and the end of the semester. Or we might put people into a driving simulator with a phone, without a phone. That would be examples for the t-test for dependent samples, because each time we're getting 2 scores for each person. For the repeated measures ANOVA, we might look at people's blood pressure at the beginning, middle, and end of the semester. Or we might go ahead and put people in a driving simulator with a phone that's handheld, with a phone that's hand-free, and without a phone. 3 different times. We'll put them in that driving simulator. Okay? All right. Now, on the other hand, the t-test for independent samples compares 2 completely different independent groups. 2 groups that do not overlap. Okay. So it could be people in your treatment group and people in your control group. It could be people with blue eyes and people with brown eyes. As long as they're 2 separate groups. This one, this t-test for independent samples, is quite similar to the one-way ANOVA. The only difference there is that you have 3 or more groups. You have 3 or more groups. So this is where we might have, let's say we're looking at if horseback riding lessons decrease anxiety, just for fun. So in this t-test for independent samples, we would have the group that gets horseback riding and the group that doesn't. In the one-way ANOVA example, we would have those who get horseback riding, those who watch a video about horseback riding but don't get the actual lessons, and those in the control group who get nothing. See how that's 3 different independent groups. We also talked about majors, right? If it was t-test for independent samples, we might compare psych majors and math majors. For the one-way ANOVA, we might compare psych majors and math majors and physics majors. And what's the problem there? What if you have a double major? Well, they can't be in this study. That wouldn't work, because then they wouldn't be independently in one group. Okay. And then finally, on the right, we have our factorial ANOVA. This is the only test we've talked about with 2 or more independent variables. 2 or more independent variables. So now we're not just going to look at whether vitamin vegemin affects energy levels, but we're going to look at vitamin vegemin and whether people are younger or older age. So we have 2 different variables that we're interested in there. All right, we're looking at energy as our dependent variable and 2 independent variables, age and taking vitamin vegemin, taking the vitamin. Okay. So that takes care of a great number of the tests that we've been talking about. Now, what if you have 2 continuous variables? Both of them are continuous. Then you know you have a Pearson correlation coefficient or a simple linear regression. One of the ways I've told you to tell the difference between these 2 is to look for the word predict. And if you see the word predict, you know it's a simple linear regression. That could be predict or predicting or predicted. But if you're trying to predict a dependent variable using your independent variable, that's simple linear regression. If you are just looking at whether two variables are associated and you're not defining the IV and DV, it's a correlation coefficient. It's a Pearson correlation coefficient. So prediction is really the key here. And like I said, notice two continuous variables. Okay. So if you've got two continuous variables, you can immediately narrow it down to two things: correlation and simple linear regression. Then to tell the difference there, like I said, look for that predict. Okay. And also, I do want to point out the IV and DV being defined is another important difference. It's just sometimes you can't quite tell that from reading a word problem. That's why I tell you to look for the word predict as well. Okay. Finally, we have zero continuous variables, right? Did you notice today that when we were doing this chi-square test for goodness of fit, all we were looking at was one categorical variable. We were looking at outcome of the rock, paper, scissors, lizard, spot game, right? So we were looking at one variable here that was nominal, categorical. It had three categories: win, loss, draw. Okay, so hang on, there's a question coming through. Yes, these tables will be on G2L for you. I will get them up for you by the end of the day today. I just wanted to go through them with you once, go through them with you once first, and I will put them up for you on D2L. So yes, you will have access to them. The zero continuous variables, let's talk about that a little bit. So chi-square test of independence, if you haven't listened to the lecture yet, let me describe how this one works a little bit for you. The only real difference is that you have two nominal variables. So let's say we were not just interested in knowing wins, losses, and draws, but we also looked at males and females, just for the sake of argument here. We can actually, with a chi-square test for independence, we don't actually have to be restricted to just two categories. So we could say male, female, and other non-binary. So we could have three there if you like. And that would work just as well. So for the number of qualitative nominal variables, you've got two. That would be gender and outcome of the game. So we would have 6 cells, right? Or 9 cells if we included the other non-binary characteristic. Let me throw another example at you. Let's say you're interested to know whether there's a color preference difference amongst people of different eye colors. Now, to keep this simple, I'm just going to use blue and brown eye colors. And I'm just going to use the color preference between yellow and red. Okay, so I want to know if people with blue eyes prefer red to yellow more than people with brown eyes. You see the idea there? I'm trying to understand the probabilities, the frequencies, how that's distributed across two different variables. Okay, so we're not going to go through all the math for the chi-square test for independence. I just want you to understand basically what one is. Okay. So those are all of the different tests we've talked about. Okay, and that's how you would differentiate them. Okay. Let's talk briefly about some statistical test interpretation as well. Okay, so if you haven't noticed, I'm kind of pulling things together for you a little bit today, so that next time can be more devoted to questions. Okay. Now, if the calculated score, and I say Z-T or chi-square because those are really the only ones we calculated here, right? You didn't hand calculate the ANOVA, and you didn't hand calculate the correlation or regression, really. But really, it's true for any test. If the score is more extreme, more positive, or more negative than the tabled value, the result is significant, statistically significant, and you're likely to reject the null. If the calculated Z, T, chi-square, any score is not more extreme than the tabled value, the result's not statistically significant, you don't reject the null. Okay. Why did I say likely to reject the null? Because remember that one exception. I'm going to skip to it. If you have a one-tailed test and the results are in the opposite direction of what's stated in the alternative hypothesis, you do not reject the null. In other words, if I said that those who take vitamin will have higher energy levels and they have lower energy levels, in fact, I'm not going to reject the null. Doesn't matter how statistically significant it wants to be. Doesn't matter how far away, how low the p-value is. I'm not going to reject. All right. So that's the by hand calculation stuff. Now let's talk about statistical test interpretation with SPSS. This is the one where we look at p-values or sig values. If our sig value is less than alpha, the result is statistically significant and you're likely to reject the null. If the observed p-value, sig value is not less than alpha, the result is not statistically significant and you do not reject the null. Why again do I say likely? For the same reason I said before. If it's a one-tailed test and things come out in the opposite direction of what you predicted, you don't reject the null, no matter what. That's the same for hand calculation and for SPSS calculation. Now, since we're summing up here, I also am going to share with you, if you remember in SPSS, there's a couple of special rules for reporting p-values. One is that if it says 0, 0, 0, you always report it as p less than 0.001. The other has to go back, or goes back to this one-tailed test idea. And it's always, SPSS is always going to give you sig values for two-tailed. So think about it for a moment. Do you remember how to go from a sig value of two-tailed to a sig value that's one-tailed? You do something simple computation to get it from two-tailed to one-tailed. And that is divide by 2. Divide by 2. So if you know you have a one-tailed test, but it's giving you a sig value, and you can obviously see, it'll tell you pretty much every time that it's two-tailed, just take that number, that p-value, and divide by 2. That will get you the one-tailed. Okay. All right. Let me open it up to any questions that you may have at this time. I will go ahead and send the link out to everyone, and I will get that the tables, I should say, posted for you guys. And don't forget that tonight, if you are interested, that's when the exam 2 bonus is due. It's due tonight. So if you haven't done that yet, make sure you finish it off by tonight. And if there are no questions, I'll just